What the hell goes on?
Some jerk shaving. Hey, cut off that lawnmower.
Relax, Junior. I got a date with the Queen of Sheba. She's allergic to beards.
Are you silly?
Take it easy. I'll fix it.
Frequency modulation, or FM, is a big step forward in radio. When you tune in, you hear what the studio mic hears. There's no static, no heterodyne squeals. The guy with the electric razor can use it all he wants. A GI can dial his girl's number. All these things in the same area, but they won't bother reception. Well, you've seen what FM means to ordinary everyday reception. But what's its military value? Just this. Until the Army turned to FM for some of its installations, radio interference was a communication headache. Sets out on the battlefield picked up static that hashed up the incoming signal. Tank tracks created static that made reception damn near impossible. Then there are teletypes, battery chargers, armored cars, tanks. The material of modern war, as well as such natural phenomena as storms, created enormous amounts of electrical interference. Frequency modulation licks this problem, and that's why we want you to know something about it. Now, the best way we can explain FM is to compare it with AM, meaning, of course, amplitude modulation. The kind that's never been able to comb static out of its hair. Now, this oscillator generates a radio wave we call the carrier. It's then fed into the amplifier where it's strengthened. But it's unmodulated, unchanging. It carries no message, or as we say, no intelligence. It's something like the steady, monotonous note of a trumpet. In order to carry a message, the wave must have the intelligence impressed on it. On AM, it's done like this. The intelligence goes into the mic as sound. The mic changes the sound into electrical energy that varies at an audio rate according to the sound. The electrical energy is fed into the modulator, where it's amplified. From here, it goes into the amplifier, where the fluctuations in electrical energy are impressed on the carrier, or radio wave, generated by the oscillator. Now, what's that mean? Well, just this. The carrier is modulated. It has its amplitude or strength changed by the fluctuating electrical energy from the modulator. Then the wave that comes from the amplifier looks like this. In this way, the carrier has its amplitude changed by the intelligence. The wave that's transmitted is an AM wave. The varying strength or amplitude of the wave carries the intelligence in AM radio. These waves are radiated by the antenna. Now, what happens in an AM receiver? First, let's take the AM wave as it approaches the antenna of our receiver. The AM receiver picks up the waves. First, it amplifies them. This way. Then it feeds them to the demodulator. The demodulator changes the RF amplitude variations back into audio frequency energy. This audio energy is built up or amplified by audio frequency stages. Then it is finally fed into a speaker, which turns it back into sound. That's how amplitude modulation works. Of course, we've gone over parts of it pretty sketchily because we're taking for granted you're fairly well grounded in AM radio by now. All's fine in AM. everything works perfectly when operating conditions are ideal. But suppose there's electrical interference of some sort. For instance, here's our transmitter and here's our receiver. Electrical impulses of all sorts produce amplitude variations in a radio wave, much the same as the audio signal in the AM transmitter over there to the left. Lightning, for instance, hitchhikes onto the transmitted wave, messing it all up, confusing the intelligence whenever it strikes. Notice how fuzzy the RF wave between the sets becomes at these times. The AM receiver can't separate the amplitude variations that carry intelligence from those that carry just noise. Noise, that's the problem. Now, what are we going to do about it? Well, we know that a radio wave has both frequency and amplitude. So far, the intelligence, represented by this audio wave, has been transmitted by holding the frequency of the carrier constant and varying its amplitude, its strength, this way. But as we've seen earlier, lightning and other electrical disturbances also vary the amplitude and upset or interfere with the original intelligence. But engineers have discovered that lightning and other electrical disturbances have a negligible effect on the frequency of a radio wave. And so they started reasoning. Why not hold the amplitude constant and vary the frequency or wavelength and make it carry the message? Where AM carries its intelligence by increasing and decreasing the strength of its carrier, this new type would do the same job by varying or modulating the frequency of its carrier. Any static that jumps onto the wave affects only the amplitude, not the frequency. The intelligence, therefore, is not affected. FM radio is based on this idea. The changing frequencies carry the message as clear as a bell. There are several types of FM transmitters used by the Army. To get a good, clear picture of frequency modulation and its general characteristics, we'd better consider a simple set first. Now, just as in AM, the carrier wave is produced, or generated, if you like, by an oscillator. In FM, this carrier wave is called the rest, or resting frequency, when it's unmodulated. That is, when there's no sound being produced. The frequency depends on the values of the coil and capacitor in the tank circuit. Change the value of either the coil or the capacitor, and the frequency changes. Now, if there were any way for the audio signal to change the coil or capacitor values, the result would be an FM wave at the output. You can accomplish this by placing a capacitor microphone in parallel with the capacitor in the tank circuit. This way. Capacitor microphones contain two plates, one of which vibrates when struck by sound waves. Of course, this rhythm is greatly slowed down. In reality, it would be anything from 16 to perhaps 16,000 vibrations per second. When the space in here between the plates varies, due to the vibration, the capacity of the mic will also vary at the same rate. Now, take this in, because it's the way the transmitter operates. The capacity of the mic affects the capacitance in the tank circuit. The capacitance of the tank circuit affects the frequency of the oscillator. The frequency of the oscillator determines the frequency of the RF wave. The RF wave is therefore frequency modulated in accordance with the vibrations of the mic plate. In other words, the frequency now varies at an audio rate when sound hits the mic. When there isn't any sound, the diaphragm of the capacitor mic keeps straight and motionless. The oscillator produces its original or resting frequency. When the first vibration of a sound wave hits the mic, it pushes the diaphragm plate closer to the stationary plate. That action increases the capacitance of the mic. This increased capacitance decreases the frequency of the oscillator. The closer the plates in the mic, the less the frequency, and the farther apart the waves. When the diaphragm moves away from the stationary plate, the oscillation increases and the waves squeeze closer together. 2 complete cycles cause the FM waves to squeeze, stretch. Squeeze, stretch. The higher the note or sound, the higher its frequency. Now, what effect does that have on the FM wave? Just this. Now, take a look at this diagram. This center line, with the figure 40 megacycles written below it, represents the rest frequency of our oscillator. Now, keep that in mind. Rest frequency, represented by this line, is 40 megacycles. That is, without being modulated, it oscillates at the rate of 40 million cycles per second. Now, what will cause it to vary from rest frequency? Any sound impressed on the capacitor microphone, of course. For example, let's say we modulate the carrier with a 500-cycle note. We get a frequency that swings back and forth above and below the rest frequency 500 times per second. Suppose we increase the frequency of the note to 1,000 cycles per second. See the difference? This 1,000-cycle note causes the FM wave to swing back and forth twice as fast as did the 500-cycle note. I know. You're wondering why these 2 notes of different pitch swing back and forth the same amount across the rest frequency. Well, that brings us to a very important point, or rather 2 points: rate of change and amount of change. You know now that frequency affects rate of change. Let's see what affects amount of change. Take the 500-cycle note again, but make it louder. Then this happens. See it? We've got the same rate of change across rest frequency, but the distance of the swing to either side of the rest frequency becomes greater. The distance is called deviation. So the frequency of a note or sound determines how many times the swing takes place, and the loudness determines the amount of swing, or deviation. Now, you can see that a great amount of deviation might cause a little trouble. That is, the deviation would go too far and interfere with another FM transmitter. So, the Army sets the maximum deviation for any channel at 40 kilocycles on either side of this rest frequency. In other words, the strongest audio signal that can be used for modulating a transmitter is one that allows only a deviation of 40 kilocycles on either side of the rest frequency. This whole thing, 40 kilocycles on one side and the same on the other, is the carrier swing. Thus, here we have a carrier swing of 80 kilocycles altogether. One more thing. There has to be a separation between channels. That is, we've got to have some method of protecting one channel from possible slop-over from another. So, here's what we do. We provide guard bands on each side of the maximum deviation. Each band is 10 kilocycles wide, making a total of 20 kilocycles. The channel allotted to each station consists of 2 deviation ranges of 40 kilocycles each, plus a 10 kilocycle guard band on each side. That's a total of 100 kilocycles. Remember, what we've seen so far is how we get the FM signal. We showed you an FM transmitter being modulated by a capacitor-type microphone because that was the easiest way of getting the point across. However, the Army uses 2 other systems of getting FM. They're called reactance tube and phase modulation.